Hello, welcome back. So we're going to take a look at another example of a line integral. So we're given the following graph. We want to evaluate the following line integral over the path supplied. So we're on C1, we're going to be on the line y equals x, and then C2, we're going to be on the line of the parabola y equals x squared. So let's see if we take a look at it. So let's see here. Let's evaluate all the parts of this real fast. So couple things. One, they give us this little value x there. That's our row. Remember, that's our row. That's our function right here. And in terms of physics, that's like our density function. This ds, that's telling me that this is the part that is our arc length. And then we're talking, we see the c right here. Remember, the c, this is the telling us we are looking for the line integral over the path. Oops, can't spell path. Over our path. So let's go ahead and see how we would solve this one. Now, the first thing we have to do is we have to change our paths into parametric. So we need C1 and C2 to convert to parametrics. And that's the first thing we're going to do here. So let's deal with C1 first. C1 is a function y equals x. Now, this is easy to convert to a parametric. We know this from pre-cal. So if we let x equal t, y is equal to t. Now remember, for y equals x, we're going to be on y equals x from 0, 0 to 1, 1. Right here. So what is that going to do? Well, that gives me my change in t's. It doesn't matter which one you use, so I'll use x. X starts at t when t would equal 0 when we start, and t would equal 1 when we end. So there we go. Now I know I'm going to be using a path, or I'm looking for that line integral, so I will need the derivatives. So I'm going to find those. X prime is 1, y prime is 1. I know I'm going to need those later on anyways. But there is our path as a parametric. We're only on this line for 1 second. For C2, we're on y equals x squared. And we're going to be on y equals x squared from 1, 1 to 0, 0. Now this is tricky because note, we switched directions. We've switched directions here. So the question is, well, what does that do for us? Well, when we do our function, the easy way to fix that is when we do our parametrics, I'm going to let x equal negative t to change my direction, to take care of my changing direction. Y will then become negative t squared, or just t squared here. So it doesn't really affect my graph, but by making that x negative, we're setting it to go in the opposite direction. So what's my change in t here? Well, looking at the t's, it's going to be, I wouldn't use the t squared because that could be kind of messy. T starts at negative 1 and we end at 0. Now this isn't the only option for us. It'll work in many different ways. But this is an easy way to kind of fix that opposite, to show we're going in the opposite direction. And again, I will need their derivatives. X prime is negative 1, y prime is 2t. Alright, so after we convert our parametrics, now we have to convert row. So converting row to a parametric, that's easy. It's just x, right? So let's see here. Now, you got to be careful. We do have two different paths. So for C1, remember we said x was t, therefore row is just t. For C2, we said x was negative t, therefore row would be negative t right here. And now I'm going to go ahead and get my line integral. And I'm going to go and write this out. My line integral should be a c. My line integral is going to equal, and I'm just going to convert this. Now there's two different ones, so I'm going to break it up. C1 x ds plus C2, path 2, x ds. Now remember, ds right now is in terms of x and y, and it's really hard to solve using function notation x and y. So that's why we converted this. So we're going to do our conversion now. So the first path starts at 0, ends at 1. My row, my x, is just t times, remember my rule, x prime of t squared, which is 1, plus y prime of t squared, which is 1, dt. Plus, do my second path. My second path starts at -1, t equals -1, and goes to 0. Row here is negative t, the square root of, this becomes, the square root of x prime squared, so that's just 1, plus y prime squared, which is this 4t squared dt. And you would solve this by hand. A couple of things here. One, you would use substitution on this one. And if you were to solve this, what you would wind up getting is 1.56, roughly around there. So let's take a look at another example. Here we have many more different curves, C1, C2, and C3. So again, we have to convert all of these into polar form, into parametric form. When looking at C1, when we look at C1, it is just a line y equals -1 from the point, looks like -2, -1, ending at the point 0, -1. Now if we notice, this is not too hard. I got to look at my x's and my y's. My y never changes. It's always just going to be -1. But what's independent is my x's. X could be anything. There's nothing here with an x, so we can just let x be t. So I can get my domain pretty easily. Ready? Looking at the t's only, goes from -2 to 0. Now, depending on what you make your x here, your t's can change. You won't get the answer wrong. I can make x be t plus 1. I would just have to reevaluate this. Get a different domain. But keep it really simple. Again, I am going to need my derivatives. X prime is 1, y prime is just 0. For C2, we are on the cubic graph. Y equals x cubed minus 1. We're starting at 0, -1, and that heads to the point 1, 0. So I am going to let x be t. My y then would be t cubed minus 1. And I can get my domain. Now remember, I could use either one of these, but that's a lot easier. If I look at the x's, x starts at 0 and ends at 1. So there's my parametric equation that will graph this part of our function right there. And of course we do need the derivatives. X prime is 1, y prime is 3t squared. C3, PO, copyright. C3 is just the line x equals 1, and that's starting at 1, 0 and ending at 1, 2. So here, x is always fixed, but y could be anything. So to get my domain, looking at the y's, starting at 0, ending at 2. So basically I'm there for 2 seconds. Now another way you can do this, you can make this more uniform. In other words, you can change your parametric, your parameters, to make it go more continuous, like especially dealing with time. -2 to 0, 0 to 1, and you can even have this one start at 1. What would you have to make this be to make this start at 1? And that's how you really got to kind of figure out what would y have to be in order to make this be at 1 right there. And then you can make it more continuous, I guess, if you like. All right, once again, we will need the derivatives. X prime here is 0, y prime is 1. All right, so once we convert this, now we got to convert our now we have to convert our row. So let's look at the rows. Row. For C1, row is going to equal, well, row is 4x cubed. We're saying x is t, so it's going to be 4t cubed. For C2, again, it's 4x cubed, and again, this is t, so again, 4 t cubed. And for C3, rho is just 1, so it's just 4 times 1 cubed, which is 4. And now I can just set up my equation, my line integral. My line integral, 0. I keep doing that. That should be just c, 4x cubed ds. There's going to be 3 of them. The first one starts at -2 to 0. My rho here, 4t cubed, the square root of, just 1 squared, right? Just 1 dt. Don't simplify. Plus my second one, right up here, our second one, starts at 0, ends up at 1. 4t cubed. And when I do this one, the derivative squared, 1 plus 9t to the 4th dt. And then my last one starts at 0, goes to 2. And what do we wind up with here? This is just 4 times the square root of, this just becomes 1 plus 0 plus 1, so it's just 1 dt. And it's not that hard to solve. You can solve this. Of course, don't forget this one here. You would use your U substitution right there. And this would wind up being a -5.733, something in there. I go to my next video. I've got one more example for you if you guys want to take a look.